Alrighty then, Physics 30. Welcome to Chapter 13, EMR Lesson 8. This will be the last lesson. We're going to finish all these slides here. We have two key things to learn in this lesson. It's about something called a diffraction grating. I've mentioned that word a few times. And then about polarization. Polarization is going to be tough for me to show you. I'm not going to worry about testing on it. But yeah, that's kind of it. So diffraction grating is essentially, instead of Young's double slit experiment, they thought, well, what if we had more slits? And then what if we had more slits? And what if we had more slits? And more and more and more and more and more. So we had a whole bunch of slits, okay, as many as we can, is up to the point that we have 50,000 slits per centimeter. Okay, 50,000 slits per centimeter. So think about that. A centimeter is about yay big. I just drew that on my iPad, maybe a little bigger than that. And there's 50,000 different little slits in there. Okay, and what this does is it basically gives us a brighter brights and darker darks. Okay, and that allows us to do a lot of things. All right, and so basically they do this by scratching very fine lines with a diamond point on glass, and they kind of go there. So compare the two splits. The diffraction grating produces interference patterns that are brighter, okay, and more defined. The more lines per grating, the narrower the fringes become. Okay, and it's different in prisms. Okay, and what it also can do this one can actually diffract using wavelengths as well, and so it's different than prisms. The red light will bend the least, and the violet light will bend the most. Okay, obviously this is something they'll talk about in diploma exams, but it's not something you need to worry about. Okay, so it's opposite in prisms. Blue bends best. In diffraction gratings, it's the opposite. Okay. All right, so diffraction gratings, we can still apply our regular Young's equations, okay, and then go ahead and do this. And what we're going to get is when we do that, we're going to get that when we have the center will still come up as white generally, but then the next ones on the outsides will go kind of have violet to red, violet to red, violet to red. Okay, so violet will always be the closest to the center. All right. So in this case, right, for refraction, right, violet gets the farthest away from the original path of the light. And in diffraction, okay, violet is the closest to the original path of the light. So just kind of keep that in mind. That's not going to be super critical, but kind of something just to be aware of, right, that these things behave differently. Okay, you can watch this video if you like. Nothing super important, but we can basically do this. Now, one thing that's going to notice is you're going to come up with this idea of 5,500 lines per centimeter. Okay, and I kind of showed you how to fix that in here. All right, and so you have 5,500 lines per centimeter, which I then just moved it into the reciprocal. So I just flipped it upside down, which means that we have 0.01 meters per 5,500 lines. All right. And so I just flipped it and turned it into meters. Okay, and I did the reciprocal. So you can do that with numbers. You can flip them. Right, if I have 5,500 number lines per 1 centimeter, I have 1 centimeter for 5,500 lines. Right, turn it into meters. And then what I'm going to do is I'm going to take the 0.01 and I'm going to divide it by 5,500. Okay, divide by 5,500. And I'm going to get this 1.18 times 10 to the negative 6 meters per line. All right, and that's good. That's the correct number. All right, that means that the distance between my lines is 1.181 times 10 to the negative 6 meters. Right, that's the distance to my line. So that's my D value when you're talking about some of these equations. All right, so I look at what I'm given. I'm given the D value here. I'm given the angle, right? It says diffracted at 50 degrees. All right, as soon as I see that diffracted at 50 degrees, I know I'm using this equation. I'm not going to be using the XD over NL one because that only works for approximately up to 10. And then it says the second order image. Okay, in order for it to be an image, it would have to be bright. And so that's one thing to notice too, is that an image occurs at a bright spot. And so therefore N would be 2. And so we go ahead, we do that. And again, keep in mind that most questions are going to be phrased in ways that they make sense when we get an answer. We get this answer of 6.96 times 10 to the negative 7 meters. If I turn into nanometers, I get 696 nanometers, which is in our range of visible light, which makes sense, right? It should be in our range of visible light. And so that's that question there. If you need to ask me questions with this, please send me an email. I'll kind of go through it again. It's something we can also go over on Thursday's meeting. All right. Things like X-rays, okay, and so this kind of applies farther. X-ray diffraction. So X-rays, we want to be able to diffract X-rays because it helps us see things like DNA. right? It's super cool. You can actually see, like, visibly see DNA. But X-rays have a wavelength that's between about 10 to the negative 10 meters. So the slits need to be much smaller than that, right? Because if you send a ray that is this big and the slit is that big, well, you're not going to get diffraction, right? So they need to be much smaller. The slits need to be way smaller than the actual ray itself, right? In order to get that, you're going to do things. So we do what's called basically a crystal, okay? And what's cool about crystals is they can kind of determine how things emerge. And you kind of get this separation and diffraction. It actually works pretty good. And it basically creates this idea of you're going to basically use interference and diffraction, but you're going to cause kind of a crystal prism method in order to cause a separation of these two waves so they do interfere with each other. It's pretty confusing, but it's also really cool. But what's also really interesting, and I want you to take note of something here, is that this gives us the concept of DNA. So this kind of math or physics principle was developed in the 1950s. All right, so this was developed in the 1950s. So we're, in the physics world, we're 70 years away from that, give or take. But in the physics world, this is relatively new physics, right? And so you guys should be seeing we're getting into more and more modern physics as we go. Okay, practice problems 36, 39. Give them a try, see how it goes. All right, we're going to finish this lesson though, or this chapter. Okay, so what we're going to do is we're going to basically we have diffraction grating, right? And it's like this. Okay, and we shine light at it. Okay, and I'm kind of drawing it as all this. When we shine light at it, the light that passes through it will have to also be orientated up and down. If I have diffraction grating that goes this way, the light that passes through it would have to also be orientated this way, right? And so what the idea is if you take a diffraction grating and a second diffraction grating and you put them perpendicular to each other over top, you actually wouldn't have very much light pass through it at all. You might get the odd dot, right? But light wouldn't really pass through it at all. And so I've shown this before. I have the experiment to show all this, of course, it's at the school. But if you want to just do a quick Google of polarization of light and look at a few things, right? Your sunglasses, they're polarized. And the idea is that it's basically going to be blocking all the light that's orientated a certain way. Okay? And so keep in mind that when a light bulb sends out rays, it can send them out flat, like this, or up and down like this, or at any angle, right? And it can be at any angle, any direction. But what we do is we use these polarizing lenses. Okay, so basically just all these lines in the same direction, right? To choose that only this light would get through. So it'd block a good chunk. And this polarization is really good. It's permanent, essentially. And once it polarizes the light, then we can actually do more stuff with it. All right. Polarization, you could do longitudinal polarization, you could do transverse polarization, but generally polarization is the same. So if we have a vertical polarizer and a horizontally polarizer, we're essentially going to get zero light pass through it. Okay, you can polarize Google image search, that kind of stuff. That's really the gist of polarization. Okay, this is the image that matters the most. This one right here. Okay, this image right here is basically I have one polarizer and one polarizer. If they're both oriented the same way, then the light will still pass through it like this. If I rotate one of them, then the center becomes black because now the back polarizer has all light passing through in this direction only, but the front polarizer only lets this light pass through. And so what that's going to do is it's basically going to give you little to no output. Okay, and that's kind of an interesting idea, is that we can actually block light more efficiently by, instead of putting a curtain up or something like that, we can actually use two polarizing things, and then as we rotate them, we can increase the amount of light and decrease them. And so this is actually kind of how we get, an eye doctor and stuff like that. You can increase and decrease the amount of light and aperture and stuff like that, and so just by rotating, right? So it's another way to block light, another way to cause light to do this. Okay, this is also applied in 3D movies. All right, this polarization and diffraction grating and stuff like that, it causes your eyes to view things at a slightly different angle. And so that allows you to have this kind of idea of three-dimensional objects, right? The old 3D glasses they had, one was red, one was green or blue. I can't remember blue. I think it did that, right? It did that. And now the new ones are actually just more polarization in general. So that's why they're kind of that darker color. Okay. LCD TVs use polarization as to bright and dark. You can read through there. It's not super critical. But yeah, that's really it. Just kind of get an idea of polarization is where we use basically the equivalent of diffraction grating to cause all the light to be in one direction. So yeah, that is the end of chapter 13. Good job getting to the end, you guys. Be getting chapter 14 going next week.